So, dear colleagues, I'm glad to present to you our teamwork with unpronounceable title. From prototypical phenomenon to dynamic functional system, I tracking data on the identification of special quadrilaterals. So my co-authors almost all are here. So there was Anna Дренева, is hiding there. And Anatolий Кричевец, and I think all you know Anna Шварц. Maybe she's. Yeah, she's. Okay, so let's start with the tasks which our participants had to solve to maybe to understand something more. There will be 4 figures, and you have to find triangle. So look at the triangle, well, into the word. Yeah, where was the triangle? maybe somebody. No, okay. That was down. We have the names. It's A, B, C, or D. So that was B. Another one to train you, maybe. So you have to find the square. Okay, square. So where was the square? It was the A. It was to the right to you, to you. Yeah. So here. Yeah. And last one. It's rectangle. Where was the rectangle? Yeah. That was the C left to the center, and right to me. Okay. So that was the task, with some differences, but I will tell you. So okay, investigations of geometrical concepts and their relations with visual representations has a long history in mathematical educational research. One of the key theoretical challenges and correspondent learning difficulties is related to the prototypical phenomena. Why is right triangle is better recognized when his had vertical legs and horizontal legs? So traditionally, geometrical concepts has been considered under the light of prototypical theory. However, this theory states, rather than explain, the mixed visual and conceptual nature of the concepts. Up to now, the difficulty to interpret the sensory cognitive dichotomy stays to be one of the major theoretical issues. In our work, we question deeper in these relations between sensory and conceptual processes in the application of categorization of geometrical shapes. So on the slide, this slide, you can see I think everybody can see the right triangle, the rectangle, the isosceles triangle, and the rhombus. And they perceived faster and more precisely than on the next slide. But they're the same figures, you know. Okay, so it's called orientation effect. So in line with the systemic structure of higher mental functions in cultural historical theory, we claim that the prototypical structure of geometrical concepts might be at least partially explained as a result of the dynamic and systemic organization of a variety of cognitive processes in an identification task. Our systemic approach highlights the tight and yet dynamical interrelations between conceptual and perceptual processes. So we use tracking data to explore the relative role of the most automized, usually pre-attentive processes, so extrafoveal perception, foveal perception, and language processes in geometric shapes recognition. So the experiment stimuli were displayed using a semi-experimental center on 21-inch monitor and 60 Hz refresh rate. Participants were seated approximately 60 centimeters distance from the monitor. Eye movements of both eyes were recorded with a sampling rate 120 Hertz by SMI rate. And 9-point calibration was considered valid if the average error in a validation test was less than 0.5 degrees, no, 0.5 degrees. So participants required to search for a shape that corresponds to the target concept. That was named before each trial. The trial were initiated by a 500 milliseconds gaze on the fixation cross in the center of screen, and the instruction was to press the space button and name the target area, A, B, C, or D, as quickly and as accurately as possible. So the researcher tracked the correctness of the response, and only correct trials were further analyzed. It's about the future analysis. The screen was divided into 5 areas of interest. Yeah, so center, A, B, C, and D. As shown in the figure. So, and we calculate the order number of first visit to the target area. So, if we assume that a participant does not use extrafoveal vision and find the target stochastically, then the mean parameter would be 2.5. If it will be stochastic sequence. So we calculated this parameter, and also we we measure the time reaction. Well, when they press the space. So and this parameter we compared with 2.5 to judge the involvement of extrafoveal analysis. First experiment, there was circle, square, triangle, and cross, and they were the target shapes. And the experiment consists of 24 trials. So the results showed clear evidence for an extrafoveal solution in task. 77.5% were solved without any fixations. So without saccades or additional fixations in another area of interest. So they just looked in the center and then press space and give an answer. So they solved 77% simultaneously or without any saccades. So in 15% of trials, we observed only one fixation, and the first fixation was immediately in the target area. So what does it mean? That the participant look in the center and then to the target area. So that means that this task solved extrafoveally. The participant already know where to look. So and there was also strong, significant individual differences in the amount of fixations needed. And this implies that in these cases, extrafoveal vision is strongly involved, but a person performs an additional saccade for a foveal check. So individual differences reveal that participants can choose more risky strategy or more safer one with an additional foveal check. Thus, the involvement of extrafoveal vision depends not only physiological mechanism, but also on personal strategies and attitude to the task. So we conducted experiment 2, our second experiment, in which we had 3 experimentally varied factors. The target concept, which can be could be a rectangle, square, or square as a rectangle. The structures that could be either similar to the target or dissimilar to the one. So you can see the examples of our trials. And the shape position, prototypical, with on their base or rotated. So we had 3 factors within subject's design with 2 dependent variables, the number of area visited and time of solving. The target area was quasi-randomized, and altogether there were 96 trials per participant. So about the horizontal and vertical or canonical orientations are the best exposed directions in human surrounding, especially if we analyze cultural environment that include buildings, furniture, and other architecture elements, artificial elements. It has been shown in many behavioral and neurophysiological studies that a stimulus with vertical and horizontal orientations is processed quicker and better in many perceptual tasks. Apparently, the better recognition of vertical and horizontal direction in comparison to others has influenced the historical development of mathematical notations such as Cartesian coordinates. So in these experiments, we investigate how this natural sensitivity to horizontal and vertical direction might contribute to the structure of geometrical concepts and presumably lead to learning difficulties. So results of second experiment. One participant gave 12 wrong answers, so we excluded her results from the group statistics. The average area was, so the average number of saccades from the center was 10.9. This. It's the average number. Both group and individual results demonstrated that it was strongly significant different from a random sequence, 2.5, or random sequence of the visit areas. And evidenced involvement of extrafoveal vision. So, but anyway, we conducted ANOVA with 3 factors: target concept, shape, target concept and shape, rotation, and distractors, similar or dissimilar to the target. All factors highly significantly influenced to the number of visited areas and reaction time. So their non-canonical rotation of the target shape and similarity with the distractors made the identification task more difficult, and the involvement of extrafoveal processes decreased. There was also an interaction between 2 factors found on both variables. And so the combination of rotation and similar distractors provided more than cumulative increase of difficulty. I think that you can see it here. So this difference is more than here. The same influences on the factors were observed on each target concept. Cross-tab analysis demonstrated strong individual differences, and this table represents results of some participants' cases. So participant A found the target shapes almost without any fixations. So it was the blue line, oh no, dark blue line, yeah. On the contrast, so only by extrafoveal vision. Participant A, on the contrast, participant D did not use extrafoveal vision much and stared at few areas before she found the target 1. It's participant D, yeah, here. So no 0 results, but here, here, here. And interesting that there are a variety of patterns, not these 2. The participant B could answer without any fixations, relying on extrafoveal vision in some trials, but needed a few fixations and foveal analysis in the others. Yeah, it's the blue line here. The results of participant C is particularly interesting. In most of the trials, she did one fixation to the target shape. Thus, extrafoveal vision was mostly reporting her the correct answer, but she performed an additionally confirmatory saccade. So that was light green here. Yeah. Okay. That's about individual differences, and let's return to the one trial, one example of trials. You have to find triangle, a rectangle, yeah, and you will have time for that. Oh, I think everybody found it. But you know that this you have to find a rectangle, but there is a square, and how these differences influence their results. Differences between number of area visited and time of solving depended on target shape. Also very interesting. Identification of a square as belonging to rectangles required more time, but did not require additional fixations. So we assume the task of identification a square as a rectangle had non-perceptual but logical difficulty for the participants. So it's that there is significant difference here, squares, rectangle, and square in time of solving, but there is no differences in number of saccades. No significant difference. Okay, so conclusions. Extrafoveal analysis is sufficient for distinguishing simple geometrical shapes, and it's substantially involved in the recognition of more complex figures. The mechanisms behind the extrafoveal processes might explain the ground of an orientation effect as part of prototypical phenomenon. The shapes in canonical orientation were mostly identified by extrafoveal vision, while in case of rotated exposure, some foveal analysis was often required. Individual differences have clearly evidenced the variety of possible strategies. Systemic and flexible organization of foveal and extrafoveal processes under the task constraints has been observed. So identification that involves inclusion relations requires additional preparations independent from the foveal and extrafoveal analysis that presumably verbally process logical relations between categories. Individual differences and flexible distribution between processes evidence the existence of a complex functional system rather than a particular stable mechanism. This functional system is dynamically constituted as an ensemble of extrafoveal, foveal, and logical processes in the response to a particular task constraints, and individual preferences. So, thank you for your attention, and
Thank you very much, Dmitry. So I'm now opening opportunity for posing questions. So starting with Dor.
Thank you very much for most interesting talk. I have a question which is coming from a mixture of my own introspection as I was thinking about the task and coming from empirical work in the cognitive sciences. Now, the task as you give it, as you state it, or as you describe it, is one of search. We are searching for the rectangle.
yeah.
But what may actually be happening is that the process, what we are actually doing. Okay, thank you. Should I repeat? Yeah. Okay. So what we may actually be doing in order to complete the search is actually tacitly, it's a matching task. Because what happens when I see the word triangle, according to research, my sense making of that word, I'm evoking an image of a triangle. Okay, so it's in my imagination, but it's quasi like a percept. All right, so that when I'm looking for the other triangle, in a sense, what's happening is a matching task between the imaginary and the real triangle that are in my field. Now, one is imaginary and one is an actual percept, but 35 years of research, beginning with Steve Kosslyn, suggest that the imaginary and the real share almost 90% of the visual cortex, of neural activity. I just wondered if you have a comment on that actually what's happening is a matching task, tacitly.
So, as I understood, you mentioned that you think that participants compare our task with his image of triangle, which he has.
Right, an imaginary image of a triangle.
Yeah.
And what we are doing when we're searching, in fact, it's tacitly a matching task.
You know, I can only give you my introspection. I'm not imaging the triangle when I just prepared to search for it.
What does that mean, to prepare to search for a triangle? I know this might be beyond the research, but I'm curious about that. What does that mean, I'm preparing?
May I have a chance to also speculate on this? I think that depending on a branch of cognitive science which we choose, we either believe that there is an imaginary triangle, or we think there are some propositional symbols, or we think there is some simulation of a previous experience. These all three possible answers, and we actually don't know. But I think that's a very important question behind it, is that even if I imagine something, do I imagine the only one particular triangle? And which one is it? And I think this kind of research shows us how complicated is this, what I do imagine there, and how differently it unlocks itself in a different kinds of tasks.
So, additional questions? Yeah, Rosa.
Okay, coming from math education, not from cognitive sciences, I think that it's also related to the definition of an object that person held. Okay, the concept image, concept definition theory. So I wonder, you, according to your reaction, you probably don't know this theory, so I can send you a paper, but I think that it's really related, this choice of objects or time that people spend for this choice, or how they analyze the objects and then have a decision. I think that it's related also to the concept image and concept definition that people held.
So I think the relations between image and the concept is the thing that we investigated here. So the relations between them is the most interesting thing, and you know, the definition. Well, the theory of prototypes is appeared well when, I think, maybe I'm speculating that when Roche saw that all we know definitions, but when we have to give an example, we all draw the same, and so on. So that is the prototypical effect.
Just to add, my view of the investigation of role of extrafoveal vision is a kind of unlocking of a perceptual mechanism behind the concept image. So what does it mean to have a concept image? And when we see that a strong and flexible involvement of extrafoveal vision, which is usually considered as an automatized with inattentive process, we see that mixture of conceptual structures and perceptual structures are really strong here. That's
Anyone else? Yeah.
In what way the results of this investigation can be useful for real practice of teaching geometry?
Good question. Well, I have to say that if we understand the mechanisms which rely under such mistakes, we can change our teaching practices. But actually, I have to say that, but I don't really believe in that. So my point of view that the zero recommendation to the learning and teaching practices is to vary. You have to vary triangles, rectangles in your textbooks, in your tasks, because the pupil have to see different rectangles, and definition is not helpful for that, or isn't helpful always, isn't always helpful.
This may be useful in fourth or fifth class in teaching mathematics?
No, I think that it is the part of a big, their action of concept. I don't know how to translate it. Подведение под понятие. Concept, no, well, okay, it's concept recognition, and it's a part of education in every part of mathematics. If you, I don't know, teach quadratic equations or so on, you always have to recognize different parts of it. Coefficient A, which cannot be yes. So that's the common mistake. So that's the and also that's the common common advice. You have to vary.
I have a fairly technical question. If you put back one of those slides with the figures on the side, you first define something. You define an area in the center.
Yeah.
And any fixation within that area is okay. There's some error of measurement. Was it half a degree?
Half a degree, yeah.
And then the foveal area is about 2 degrees. So how far would it reach the sharp vision in maximum in that area if you are at if the fixation is at the very edge, and there's a half a degree error, and you count one more on the radius? So
in our thesis there are measurements of degrees, but I don't remember the center part. What was the center part? But I don't think. Also,
I see it relevant for some things. So let me say, not in this, but when you have a circle in there as a recognizable object.
Well, okay.
A circle can be recognized with just seeing a part of the curve, because it's kind of prototypical part always. Whereas for identifying rectangle and square requires that you have to see the other, like further back. So did you see any difference between what kind of object was to be recognized how easily it was recognized extrafoveally?
Well, in that experiment, I think no, we didn't. We don't. We didn't. Check these differences, but you know the numbers here, they more than 90% with one saccade or without saccade is very I don't know. Well, okay, so it's clear to me, and maybe to you that.
That's a good question, in fact, because indeed, if you go on the border of a central center, then the border of a figure might be on the border of fovea. And it is true, but it's a border of border of border. The distance was more than 5 degrees between figures. So it's border, border, border thing. And with this particular stimuli, the results are very clear. They are just looking in the very center. Very, very center, very clearly looking, and no eye movements at all. So it's mostly, yeah, you can do that.
Yeah, thank you for clarification. Anyone else? Any other aspects to that?
I think we can start to prepare you for the next chapter.
Yeah, so you have 10-minute break before the next presentation. This extended break now because we're finishing a bit early. I think it's always more difficult to discuss this kind of technical research. I think it's really exciting, but also personally, I don't have any more questions because it's
Very clear.
It's very, yeah, it's very clear. It's very fact-based. There's not much elaboration about the interpretations. So thank you very much. Thank for the whole team. You're doing a wonderful job.